here's the equation we had on the last video, right here. And this is obviously, this, which we already solved the quadratic equation for this. So we're going to kind of use that same piece of information. So if for some reason you didn't watch the last video, make sure you go back and watch it before you watch this one, or else it's going to be sort of lost. But we solved the quadratic equation and we got these two responses. Now we have here the same quadratic equation. Now I'm actually going to kind of retroactively write something that gives me this vertical displacement equation. So, like for example, let's say it's a baseball. Okay. No, it's a bouncy ball because I want to see how high it's going to bounce. A bouncy ball is thrown from a bouncy ball cannon at, alright, and what I did here was, okay, I know that I need the vertical component to be 20. Alright, well if you take the inverse sine of 1/2, let's say I want to make it actually twice as much, so basically, if you take the inverse sine of 1/2, you get 30 degrees. So I'm going to make the angle 30 degrees, and again, that's going to give me half of the full velocity, so I'm going to put 40. A bouncy ball cannon at 40 meters per second with an angle of 30 degrees. From an initial height of 200 meters. Alright. Point is, you can try this out. If you just took that equation there, you're like, okay, I'm going to use this information, write a vertical displacement equation, you should get the same thing. Because when you find the vertical component, when you take 40 times the sine of 30, you're going to get 20 back out. Alright, and that's why this is 20. Of course, the height is there. And this is, whoops, I still didn't change this, right? Negative 4.9 t squared. Because that's just, again, gt squared over 2, which is never changing. Alright, so this is the equation. And this is our vertical displacement equation. Now, again, we're using the same solution from last time. We got that it hits the ground after. We found out actually it's ground at 8.74 seconds later. So just sort of visually, this object is going to be, it's going to be launched. This baseball is going to be, it starts from way up here, and they're going to launch it up, and then we got to figure out, okay, we know it hits the ground after, let me double check, 8.74 seconds. Yes. So we know it hits the ground after 8.74 seconds. And again, we're going to assume, of course, this doesn't really make much sense for a bouncy ball, but we're going to assume that it doesn't move after it hits the ground. Just thud. Maybe it sticks in the mud or something down here, but it's just going to hit the ground and it's going to stay there. So we want to know what is the range. In other words, what's the distance from it? Let's say if it's from 200 meters, maybe it's in a plane or something. Somebody threw a bouncy ball out from a plane. There we go. Yeah, I know what you think that looks like, but it's a plane. Alright, we throw it out, and the range is really this distance here, the distance from here to here. That is the range. That's what we mean when we say range. How far is it going to go? Or in other words, if I could figure this out before, right, because all these initials are set, I could say, okay, well, I need you to stand here with your glove, and you're going to catch this bouncy ball. So to figure that out, the actual range, we have to use this piece of information, 8.74 seconds. And think about it. We've been talking about the vertical velocity, right? We've been talking about this is describing only how it's moving up and down. But obviously it's also moving side to side. Well, how is it moving side to side? That's the horizontal component. So let's find out what the horizontal component of this equation is. So for the horizontal component, Vx, I know we haven't used it in a while, which is what I was saying. You don't use it a lot, but here we do use it. Vx is going to be V times the cosine of theta. So Vx is going to be the velocity times the cosine of the angle. So you got to punch that in a calculator, 40 times the cosine of 30. And I get 34.64. Alright, so that's the velocity, 34.64 meters per second. That's how fast it's moving horizontally. In other words, every second that it's in the air, it's going to go 34.64 meters. That's what 34.64 meters per second means. Now, how do you think we can find how far it goes in 8.74 seconds? Of course, we just take this velocity and multiply by that time. Right? That goes way back to speed, distance, time. Remember, we had this whole equation, distance is speed times time. That's pretty much what we're doing. Take your speed, in this case it's a velocity, and multiply it by your time, 8.74 seconds. So the total range, the distance it's going to travel is just going to be 8.74 times 34.64. Let's see what we get. Okay, so I plugged that in, and from our range, I get 302.7, we're now at 302.8 meters. And that's my answer. 302.8 meters. Not that difficult, right? This part is easy, right? It's really just multiply two numbers. Take your time, multiply by this, the horizontal component. That part's easy. It's the part before that really takes your time, right? This is what took us our time. And that's where, if you do a range problem, that's where you're going to be spending probably 75, 80% of your time, is actually finding when does this hit the ground. Because again, if you know when it hits the ground, it's just take that time times the horizontal speed and you're done. That's the horizontal distance, or the range, horizontal displacement. Yeah, but that's it, okay? So again, it may take you a little practice just because these do take a long time. The problems are kind of long, but hopefully you understand kind of, my goal is at the end of this series of videos that you see a couple of things. I want you to be able to see, okay, well, we can use this equation to figure out when this object's going to hit the ground, right? This vertical displacement equation. And if we know, if we can write this equation, in order to solve it, we have to use complete the square. And I know we're using the quadratic formula, but I showed you that quadratic formula is complete the square. That's the only way, really, to solve these, unless you get a really nice one that you can just factor out visually. But those are few and far between, especially when you're dealing with negative 4.9. It's just not going to happen. So you have to do complete the square. And when you use complete the square, you get this quadratic formula. When you use the quadratic formula, you can figure out when this hits the ground, or in other words, when this is equal to 0, right? When does this hit the ground? And so once you know when it hits the ground, then you just can figure out the range by taking the velocity and multiplying by how long it was in the air, right? So it's kind of easy to sum up, but understand there is a lot of work in those steps.